Good day. So today we are to discuss the Newton's law of cooling. For example, let's have this expression. This is the change in temperature with respect to the change in time is directly proportional to the difference of the temperature of the body under consideration and the temperature of the surrounding medium. So let's say this T, uppercase, is the temperature of the body or the object under consideration, and T sub m will be the temperature of the surrounding medium or the ambience. Okay, so for us to have an equation, this is the change in temperature with respect to the change in time. We are to place a proportionality constant. Okay, multiplied by the temperature of the body, less the temperature of the surrounding medium. But for the case, for example, if the temperature of the body is higher than the temperature of the medium surrounding, it will result to cooling. So cooling means this is a decrease in temperature, or that is, if we say decrease in temperature, it should be a negative change in temperature. So how do we express that case? So all we have to do is place a negative sign before our proportionality constant. Okay, so for that case, if we have a greater temperature of the body than its surrounding, the effect is cooling, and it will give us a negative rate of change of temperature. So how to express that? I will place a negative sign for the proportionality constant. Then we simplify, or we are now to solve for the solution. So this is now the change in temperature. So this is by cross multiplication. This is to be divided by the temperature minus the temperature of the surrounding medium is now equal to the negative k multiplied by the change in time. So we are now to integrate both sides of the equation. So integrating both sides of the equation, what is the integral of dt over t minus t sub m? So this is the same as, basically, if we are to recall our integrals, the ln, our natural logarithm of t minus t sub m, is now equal to, this is negative k, the integral of dt is t plus the arbitrary constant. So for us to remove this ln, we are to use e. This is now e raised to the ln multiplied ln of t minus the t sub m is now equal to, this is e raised to negative k times t plus c. But we know that the base of ln is e, so we can cancel this one. So this is the same as the t minus the t sub m is now equal to, how do we simplify? If we are adding exponents, which means we have the same base. So the base of e, this is negative k, a base of e raised to negative k times t. Again, if we are adding exponents, we have a common base. This is also to the base e raised to c. But we know that e raised to a constant is simply constant. Okay, so we can now simplify our working equation. This is now the t minus the t sub m is equal to, so we bring, this is the same as constant c, the constant c times e raised to negative k times t. So we have the temperature as a function of time is now equal to c, e raised to negative k times t plus the temperature of the surrounding medium. So let this be our working equation. So let's have an example. By the way, for the case that we have, or if the process will be, let's say, cooling, if there will be a cooling, so we are to use negative k. If we have increase in temperature or heating, we are to use positive K. So let's have an example. Okay, so let's have an example. Okay, a boiling solution that is at 100 degrees Celsius is set on a table where the room temperature is assumed to be constant at 20 degrees Celsius. The solution cooled at 60 degrees Celsius after 5 minutes. Letter A, find a formula for the temperature of the solution after it is placed on the table. So let's have, or we are to look for its working equation. So let us look for the given. Alright, so according to the problem, that is initially or at time is equal to 0, we have that initial temperature that is equal to 100 degrees Celsius. So taking note that we are bringing a boiling solution to a room temperature, or to a room with a temperature of 20 degrees Celsius. So which means this case is basically cooling. So this is cooling. So let's have our working equation, that is the temperature is equal to, or that is the temperature as a function of time is equal to C, this is e raised to negative k, multiplied by the time, plus the temperature of the surrounding. So we have the temperature of the surrounding, or the temperature, that is the room temperature, equal to 20 degrees Celsius, and it is constant. So let's have this given. That is, at time is equal to 0, the temperature is 100 degrees Celsius. So by substituting, this is 100 degrees Celsius is equal to C. This is e raised to negative k. At time is equal to 0, plus the room temperature, that is 20 degrees Celsius. So we have 100 less 20, that is the same as 80 is equal to C. This is e raised to, so we know that negative k times 0 is 0. Any value raised to 0 is the same as 1. So we may remove this e. So basically, the value of our constant will be, the value of the constant will be equal to 80 degrees Celsius. That will be the value of the constant, or simply 80. Just to avoid confusion, using C. Then we have, according to the problem, the solution cooled to 60 degrees Celsius after 5 minutes. So let's have, at time is equal to, we are using time in minutes. At time 5 minutes, the temperature now is equal to 60 degrees Celsius. So we are to substitute, since we have now the value of the constant C, this is 80. So from our initial working equation, this is now 60 is equal to, what is the value of C? We have that as 80. This is e raised to negative k, multiplied by the time. This is now 5 minutes, plus our room temperature, which is constant, that is 20 degrees Celsius. So we'll be having 60 less 20, that will be 40 is equal to 80. This is e raised to negative k times 5. So dividing both sides of the equation by 80, so we have 40 over 80, simply 1/2 is equal to, this is e raised to negative 5k. So for us to solve for the value of the proportionality constant k, we may use our natural logarithm. This is the ln of 1/2 is equal to the ln of e raised to negative 5k. So we know that since we are using natural logarithm, we can now bring down this exponent. So this is ln of 1/2 is now equal to negative 5k. This is multiplied by the ln of e. So we know that the value of ln of e is the same as 1. So computing now for the value of the proportionality constant k, dividing both sides of the equation by negative 5. So what will be that value? This is the ln of 1/2 or 0.5. This is divided by negative 5. The value of k will be equal to, so if you are to use 4 decimal places, let's say that is 0.1386. This is 0.1386. So that will be the value of the proportionality constant. So since we have now the value of the constant c and the proportionality constant k, so let's have our working equation or the expression for the temperature at any time t. That is the required for letter A. So this is for letter A. Again, from our initial equation, that is the temperature at any time t is equal to c. This is e raised to negative k time plus the t sub m. So this will be the time as a function of time. The temperature as a function of time is equal to c. That is 8t. This is e raised to negative. The value of k is 0.1386 times the time plus our room temperature, which is constant, that is 20 degrees Celsius. So this will be our working equation. The working equation for letter A. So the formula for the temperature at any given time t. So what about for letter B? I determine how long will it take for the solution to cool to 22 degrees Celsius. So we are looking for the time. This is for letter B. We're looking for the time if the temperature now is now equal to 22 degrees Celsius. So what is our working equation? So we are just to copy this equation. So the temperature at any given time t is equal to, this is 8t, e raised to negative 0.1386 times the time t plus 20 degrees Celsius. So the temperature is 22 degrees Celsius. So that is we are writing 22 equal to 8t. This is e raised to negative 0.1386. Again, we are using a negative sign for k since this is cooling. Times time t plus 20. So we are now solving 22 less 20. That will be 2 is now equal to 80 times e raised to negative 0.1386 times the time t. So dividing both sides of the equation by 80. So 2 over 80 is basically 1 over 40 is now equal to e raised to negative 0.1386 times the time t. So we are solving for the time t. Let us use a natural logarithm. This is now the ln of 1 over 40 is equal to the ln of e raised to negative 0.1386 of the time t. So since we are now using ln, we can now bring down this exponent. So this is now the ln of 1 over 40 is now equal to negative 0.1386 of the time t multiplied by the ln of e. So we know that the value of ln of e is the same as 1. So dividing both sides of the equation by negative 0.1386. So dividing both sides of the equation by negative 0.1386, that will give us the value of time in minutes. So this is the same as the ln of 1 over 40 to be divided by negative 0.1386. 86. Oh, syntax error. That is 26.6153 if I to use 4 decimal places. This is 26.6153 in terms of the time minutes. Let us double check the value. 26.6153 minutes. So this will be our solution. So after or on the time of 26.6153 minutes, the temperature will be now at 22 degrees Celsius. So this will be our solution for this example. Alright, so let's have another example. So a body at a temperature of 50 degrees Fahrenheit is placed outdoors where the temperature is 100 degrees Fahrenheit. If after 5 minutes the temperature of the body is 60 degrees Fahrenheit, letter A, how long will it take the body to reach a temperature of 75 degrees Fahrenheit? And letter B, the temperature of the body after 20 minutes. If we are to observe the situation, so this body has a lower temperature. So let's say this is at time is equal to 0. And the temperature of the body is equal to 50 degrees Fahrenheit. Wherein the temperature of the surrounding, or that is outdoors, the surrounding medium, is 100 degrees Fahrenheit. The temperature of the surrounding medium is greater than the temperature of the body. So if we are to place an object in a hotter environment or in an environment with a higher temperature, it is expected that the temperature of the body will rise. So basically, this case is heating. Okay? So for letter A, how long will it take for the body to reach a temperature of 75 degrees Fahrenheit? So first, we need to have our working equation. So we have, from our previous derivations, we have the temperature at any given time t is equal to C. This is e raised to, this time, we are using positive K since this is heating. So leave it as K. So positive K times T plus the temperature of the surrounding medium. So from this given, at time 0, the temperature is 50 degrees Fahrenheit. So this is 50 equal to C. This is e raised to Rk at time 0 plus our initial, the temperature of the surrounding medium is 100. So we know that e raised to 0 is 1. Any value raised to 0 is 1. Then we have 50 less 100. I will be having the value of the constant C as 50 minus 100, that is negative 50. Then we have another set of given, that is after 5 minutes, the temperature is now 60 degrees Fahrenheit. So let's say this is at time is equal to 5 minutes. The temperature is now equal to 60 degrees Fahrenheit. Sorry, so this a correction. We are using degree Fahrenheit, not degree Celsius. So this is 100 degree Fahrenheit. So this is 60 degree Fahrenheit. So we are to substitute in this our initial derivations. So we have the time is 60 degree Fahrenheit is now equal to C. The value of C is negative 50. This is now e raised to negative, or this is e raised to k at time 5 minutes, plus the outdoor temperature is 100. So this is 60 less 100 is negative 40 is now equal to negative 50. This is e raised to 5 k. So dividing both sides of the equation by negative 50, this is now equal to negative 40 over 50 is positive 4 over 5 equal to this is e raised to 5k. So solving for the value of the proportionality constant k, a natural logarithm, this is 4 over 5 equal to this is the ln of e raised to 5k. So we are now bringing down this exponent. So this is the ln of 4 over 5 is now equal to 5k ln of e. So we know that ln of e is the same as 1. So dividing both sides of the equation by dividing both sides of the equation by 5, the value of the proportionality constant k is now equal to this is the ln of 4 over 5 all over 5. That is negative 0.446. If I to use 4 decimal places, negative 0.0446. Let's check. So negative 0.0446. So we have now the value of the proportionality constant k, the constant c. We can now have our working equation. Alright, so our working equation. Okay, from our derivation, we have the time, the temperature at any given time t is now equal to c. This is e raised to k, again, positive k this time since this is heating times time t plus the surrounding medium temperature. So this is the time, the temperature at given time t. I keep repeating that mistake. So we have the temperature at a given time t, the value of c is negative 50. This is e raised to, the value of k is negative 0.0446 of the time t plus our initial temperature of the environment or the surrounding, that is 100 degree Fahrenheit. So plus 100. So this will be our working equation. So we are expecting that the temperature of the body will rise since its environment has a higher temperature. So letter A, how long will it take for the body to reach a temperature of 75 degree Fahrenheit? Again, this is for letter A. We are looking for the time when the temperature is now at 75 degree Fahrenheit. So all we have to do is substitute this 75 degree Fahrenheit in our working equation. So this is 75 degree Fahrenheit is now equal to negative 50 e raised to negative 0.0446 times the time plus 100. So what is the value of 75 less 100 is negative 25 equal to negative 50. This is e raised to negative 0.0446 of the time. So dividing both sides of the equation by negative 50. So we simplify. Negative 25 over negative 50 is simply positive 1/2 equal to e raised to negative 0.0446 of the time. Using natural logarithm, ln of 1/2 is now equal to, this is e raised to, or ln of e raised to negative 0.0446 of the time. So we bring down this exponent. So this is now the ln of 1/2 is now equal to negative 0.0446 of the time ln of e. So ln of e is the same as 1. So solving for the time, so we divide both sides of the equation by negative 0.0446. Okay, so computing for the time is now equal to, this is the same as the ln of 1/2 or ln of 0.5 or 0.5 divided by is negative 0.0446. That is 15.5414. This is 15.5414. Let us double check the value. 15.5414. So in terms of minutes. So for letter A, it will take 15.5414 minutes to reach a temperature of 75 degree Fahrenheit. And then we proceed to letter B. The temperature of the body after 20 minutes. So we are looking for the temperature of the body after 20 minutes. So this is letter B. The given time is 20 minutes. And this time we are looking for the temperature. So we substitute that to our working equation. This is the time at 20 minutes is equal to negative 50 e raised to negative 0.0446. The time is 20 minutes plus 100 degree Fahrenheit. So this will be the temperature after 20 minutes. This is negative 50 shift e raised to negative 0.0446 times the time 20 minutes plus the temperature of the surrounding medium, that is 100 degree Fahrenheit. So let's say this is 79.5082. 79.5082 degree Fahrenheit. So this will be our answer for letter B, the temperature at 20 minutes. So this will be our solution for this example.